Something is out there, and Voyager 1 is listening to it right now. Not a malfunction, not a glitch, not a technical anomaly that engineers can dismiss with a press release and a firmware patch. A sound, a persistent, unrelenting, narrowband hum, bleeding through the instruments of the loneliest machine humanity has ever built. From a place so far away that the signal you're hearing right now left that spacecraft before yesterday even began. And nobody, not NASA, not Cornell University, not the most sophisticated astrophysicists alive, can fully explain what is producing it. That silence from the experts, that is the part that should terrify you. There's a number that most people will never truly feel in their bones. 25 billion kilometers. That is not a distance you can drive. That is not a distance you can fly. That is a distance so incomprehensible that if you tried to walk it at a steady human pace, without stopping, without sleeping, without eating, you would still be walking long after every person alive on Earth today had already turned to dust. That is where Voyager 1 is right now. And that is where the story begins. Not with a launch, not with a mission briefing, but with a sound that no human ear was ever supposed to hear. NASA's Voyager 1 spacecraft is now so far from Earth that a radio signal traveling at the speed of light, the fastest thing in the known universe, takes more than 23 hours to make the one-way trip between the probe and our ground stations. Think about what that means. When engineers at NASA's Jet Propulsion Laboratory in Pasadena send a command to Voyager 1, they do not get an answer the same day. They send a message into the void, go home, sleep, wake up, have their morning coffee, and only then, if everything goes perfectly, does a whisper of a response come crawling back across the darkness. And that gap is growing wider every single day. By late 2026, on the team's own projection, that one-way signal time will reach roughly 24 hours, making Voyager 1 the first human-made object to sit approximately one full light day from Earth. One light day. The speed of light, sustained for an entire day, and you still have not closed the gap. Humanity built this machine with slide rules and vacuum tubes and the sheer, stubborn will of engineers who refused to accept that space was too big to touch. And now that machine is so far gone that it exists in a category of distance that has no human reference point whatsoever. But here is where it gets strange, because Voyager 1 is not silent out there. It is listening. And what it is listening to has scientists at some of the most respected institutions on the planet genuinely unsettled. In one of its most recent transmissions, Voyager 1 recorded a persistent hum of interstellar plasma, a steady background hiss that may represent the actual background noise of our galaxy, something no instrument had ever been close enough to capture before. Sit with that for a moment. The background noise of the galaxy. Not a star, not a planet, not a solar flare or cosmic ray burst or any of the dramatic, violent phenomena we normally associate with space. Just a hum. Quiet. Continuous. Ancient. The kind of sound that has been vibrating through the fabric of interstellar space for billions of years, and that we are only now, only because one small machine survived long enough and traveled far enough, beginning to hear for the very first time. Scientists from Cornell University published findings confirming the detection of a class of very weak, narrowband plasma wave emission in Voyager 1's data that persists continuously from 2017 onwards, enabling the first steadily sampled measurement of interstellar plasma density over approximately 10 astronomical units, a span of space that dwarfs any previous direct measurement humanity has ever taken. The word that matters most in that sentence is not detection. It is not plasma. It is not even interstellar. The word that matters most is persists. This hum does not come and go. It does not spike during solar events and then fade back into silence. It is always there. It has been there every single time Voyager's instruments have been listening, which raises a question that nobody in mainstream science coverage seems to be asking loudly enough. What exactly is generating something that consistent, that unrelenting, in the deepest emptiness between the stars? James Cords, a professor of astronomy at Cornell University, described the sound as resembling a quiet or gentle rain, with solar outbursts appearing on top of it like lightning bursts in a thunderstorm, and then the rain returning again. That is a beautiful metaphor. But think about what it implies. If solar outbursts are the lightning, violent, temporary, explosive, then what Voyager is hearing between those bursts is something altogether different in character. Something that was already there before the sun's influence reached it. Something that will still be there long after the last ripple of solar energy fades. The interstellar medium, the vast, near-vacuum ocean of gas, plasma, magnetic fields, and ancient stellar debris that fills the space between star systems, has its own voice, and we are only now beginning to hear it. And this is where everything changes. Because Voyager 1 was never supposed to last this long. It was never supposed to go this far. When it launched in September of 1977, when Elvis Presley had been dead for less than a month, when the first Star Wars film had just reached theaters, when personal computers were still a novelty and the internet did not exist, the mission plan called for close-up photography of Jupiter and Saturn. That was it. 2 planets, a handful of years, A defined, bounded mission with a beginning and a planned ending. Nobody at NASA in 1977 sat down and seriously budgeted for a spacecraft that would still be functioning in 2026, 49 years later, transmitting data from a place that is not technically inside any star system at all. This was not the plan. What Voyager became is something far beyond any plan ever drawn. Along with returning the first detailed close-up images of Jupiter, Saturn, and their moons, Voyager 1 became the first human-made object to cross into interstellar space, a milestone that remains astonishing when you consider the distances involved. But the crossing itself, the moment in 2012 when Voyager 1 punched through the heliopause, the boundary where the sun's solar wind can no longer push back against the cold pressure of interstellar space, that crossing revealed something that shook the scientific community's assumptions to their foundation. The boundary was not what anyone had predicted. The interstellar medium beyond it was not the quiet, passive void that models had suggested. It was turbulent, dynamic, electrically alive in ways that no theoretical framework had fully anticipated. What Voyager 1 confirmed after crossing the heliopause is something scientists had long theorized but never actually established, that the interface between our solar system and the cold expanse of interstellar space is far more dynamic and violent than anyone had ever imagined. The models were wrong, the textbooks were incomplete, and the machine that revealed this was a 49-year-old spacecraft running on a nuclear battery the size of a car engine, built with 1970s technology, communicating across 25 billion kilometers through an antenna that generates less radio frequency power than a household refrigerator light bulb. Read that again. Less power than the bulb inside your refrigerator. And yet the signal gets through, because the universe, for all its chaos, is at least consistent enough to let light travel in a straight line. But what Voyager is now detecting goes deeper than the turbulence at the boundary. Astrophysicists are actively considering the possibility that Voyager 1 may have entered an unknown wave structure in the interstellar medium, or maybe passing through remnants left by a supernova explosion that occurred billions of years ago, meaning that the faint waves being captured by the probe's instruments may have been generated by a stellar death millions of years before our solar system even formed. The machine built by human hands in a decade when people were still calculating trajectories with paper and pencil may currently be detecting the echo of an event so ancient that it predates the Earth itself. There are no words in any language adequate to the weight of that idea. But here is where it gets worse. Because right now, in April of 2026, the team responsible for keeping Voyager 1 alive made a decision that tells you everything about the knife-edge situation this mission is operating under. On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory sent commands to shut down one of Voyager 1's science instruments, the Low Energy Charged Particles Experiment, or LECP, which had been operating almost without interruption since Voyager 1 launched in 1977, nearly 49 years of continuous operation. 49 years. That instrument had been alive and measuring for 49 years, through every planet flyby, through the crossing of the heliosphere boundary, through the transition into true interstellar space, through every technical crisis and every firmware patch and every anxious night the engineering team ever spent wondering if this would be the day the signal finally stopped. And now it is off, not because it failed, but because the power budget no longer has room for it. Voyager 1 now carries only 2 remaining operational science instruments, one that listens for plasma waves and one that measures magnetic fields. And engineers believe the latest shutdown could buy the mission roughly another year of operational breathing room. 1 year. That is all the margin left. 1 year of power stretched across one of the most scientifically significant missions in human history, and the people managing it are making impossible choices about what to sacrifice and what to save. And what they chose to save, what they decided was worth keeping alive above everything else, was the instrument that listens, the plasma wave sensor, the ear that is pressed against the galaxy and hearing that hum. That choice was not accidental. That choice tells you exactly how important this signal is to the people who understand it best. Voyager. 1 still has 2 remaining operating science instruments, one that listens to plasma waves and one that measures magnetic fields. They are still working great, sending back data from a region of space no other human-made craft has ever reached, according to NASA's official communication on the shutdown. A region of space no other human-made craft has ever reached. That phrase is used so casually in the NASA press release that it is easy to scroll past it without registering what it actually means. There is no backup instrument. There is no second probe positioned nearby to cross-check the readings. There is no way to send a repair team. What Voyager 1 hears, it hears alone. What it reports back is the only direct measurement of that region that will exist until some future civilization, possibly not even our own, manages to send something else out that far. And the pathway to that data is more fragile than most people realize. Deep Space Station 43 in Canberra, Australia, the only antenna in NASA's network capable of sending commands to Voyager 1, was taken offline from May 2025 through February 2026 for major upgrades, leaving only bridging communication capacity during that window, the only antenna on the entire planet. The single point of contact between humanity and its most distant creation, taken offline for 9 months for maintenance. If something had gone wrong with Voyager during that window, if an onboard system had failed or a course correction had been needed or the power management had required emergency recalibration, the response time would have been catastrophically compromised. We had one thread connecting us to the farthest object humanity has ever placed in space. And for 9 months, even that thread was stretched dangerously thin. This is not a story about a space probe. This is a story about the absolute limits of human reach, about what it means to build something, send it away, and then spend half a century trying desperately to keep listening to it as it falls further and further beyond the edge of everything you know. The engineers at JPL who work on Voyager are not glamorous figures. They do not get the headlines that Mars mission teams get. They do not have the photogenic drama of a rocket launch or a rover selfie on a red desert horizon. What they have is quieter and stranger and somehow more profound than any of that. They have the sound of a machine they will never touch again, sending back a whisper from a place no one has ever been, and the daily, grinding, technically brutal work of keeping that whisper alive for one more day. The team is also developing a more sweeping power conservation plan they informally call the Big Bang, a coordinated swap of several powered components all at once, trading older systems for lower power alternatives. And if testing on Voyager 2, planned for May and June of 2026, goes well, the same procedure will be attempted on Voyager 1 no sooner than July of 2026. The Big Bang. They named their last resort power overhaul after the origin of the universe. Whether that is irony or poetry, the engineers at JPL have earned the right to call it whatever they want, because what they are attempting has never been done before. A remote surgery performed across 25 billion kilometers on a patient who cannot be touched, whose vital signs take 23 hours to reach the operating room, and whose only chance of survival depends on everything going right the first time. There is no second attempt. There is no do-over. There is only the command, the wait, and then whatever signal comes back, or does not come back, across that impossible distance. But here is the deeper question that all of this engineering drama sits on top of. Why does it matter? In a world of James Webb Space Telescope images that make people gasp, in a world of Mars rovers and private moon missions and orbital space stations and commercial launch vehicles stacking up on pads in Texas and Florida, why does a 49-year-old spacecraft on its last legs, carrying instruments designed before the microchip was a consumer product, still matter enough that NASA is performing a power management surgery of unprecedented complexity just to keep it going? The answer is not sentiment. Scientists are not sentimental about hardware. The answer is that Voyager 1 is doing something that nothing else can do. It is giving us direct, in situ, real-time measurements from the interstellar medium. Not from a telescope, not from a theoretical model, not from computer simulations of what scientists believe should be out there, from the place itself. The emission detected by Voyager 1's plasma wave system, persisting continuously since 2017, enables the first steadily sampled measurement of interstellar plasma density over approximately 10 astronomical units, revealing density fluctuations that trace turbulence in the interstellar medium in a way no previous observation had been able to capture. 10 astronomical units of direct measurement. Each astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers. Voyager 1 has been mapping turbulence in the interstellar medium across 10 times that distance, continuously, for years. That data does not exist anywhere else. It cannot be replicated from the ground. It cannot be generated by the most powerful telescope ever built. It comes from one source, carried on one aging spacecraft, sustained by one shrinking nuclear battery, and sent back across one fragile radio link that takes almost a full day to bridge. This is the only data of its kind in existence. And what that data is telling us about the universe we live in is genuinely unsettling in the best possible way. The interstellar medium is not empty. It is not a passive vacuum through which stars move like ships through a calm sea. Interstellar space is dominated by the plasma, ionized gas that was ejected by the death of nearby giant stars millions of years ago, and the environment beyond our solar bubble is fundamentally different in character from the environment inside it. Everything we know about space from inside our solar system, every observation, every measurement, every model, is filtered through the heliosphere, the vast magnetic bubble that the sun blows around itself and everything orbiting it. We have been looking at the universe through a window our entire history as a species, and we did not even fully understand the nature of that window until Voyager crossed it. Now, for the first time, we have measurements from the other side, and the other side is alive with a complexity that our models consistently underestimated. Scientists have noted that the noise Voyager is detecting follows patterns unlike those associated with any known cosmic phenomena, such as solar winds or standard cosmic rays, a regular structure that does not match any previously cataloged interstellar signal type. Not solar wind, not standard cosmic radiation, not the electromagnetic signature of any known astrophysical process that should be occurring at that location in interstellar space. The signal has a structure, it has a regularity, and regularity in physics is never accidental. Regularity means a mechanism, a process, a cause that repeats. And the scientific community does not yet have a complete, agreed-upon explanation for what that cause is. Some believe it is quasi-thermal noise from the plasma itself, a natural byproduct of charged particles vibrating in the interstellar electric field. Others think it may represent wave structures seeded by ancient supernova shockwaves, still reverberating through the interstellar medium billions of years after the star that caused them died. And then there are the astrophysicists who, very quietly, very cautiously, note that the alternative explanations have not yet been entirely eliminated, and who choose their words carefully when discussing what else, theoretically, could generate a narrow-band, persistent, structured emission from the deepest interstellar space. Nobody is using the word contact. Nobody in a peer-reviewed paper. Nobody in an official NASA briefing. Nobody with a reputation to protect is making that claim. But the scientific process is built on eliminating possibilities one by one until only the truth remains. And as of right now, the full elimination of every non-natural explanation has not been published. Voyager has only been designed to detect the natural sounds of interstellar plasma, and was never built to transmit or interpret signals of external origin, which is precisely why the persistence and structure of what it is detecting is so uncanny to the researchers studying it. It was not designed to find anything unusual. It was designed to measure what the models said should be there. And what it found instead is something the models did not fully predict and cannot yet completely explain. There is something almost philosophically devastating about that gap. We built a machine to confirm what we already believed, and it came back with data that forced us to revise what we believed. That is science working exactly as it should. But it is also a reminder, one that comes from 25 billion kilometers away and takes 23 hours to arrive, that the universe is not obligated to conform to our expectations. It does not care about our models. It does not schedule its phenomena around our understanding. It simply exists in all its turbulent, humming, ancient, unimaginably vast complexity. And every once in a while we manage to stick a small metal ear against it and hear something new. Both Voyager 1 and Voyager 2, now the only two active spacecraft operating in true interstellar space, are in the final years of their operational lives, with power management decisions growing more consequential with each passing month. When they go dark, and they will go dark, possibly within this decade, there will be a silence unlike any we have experienced since the space age began. Not the silence of a mission ended. The silence of years removed from a place we cannot easily reach again. The next mission capable of reaching interstellar space and transmitting data back would take decades to plan, fund, build, and launch, and then decades more to actually travel the distance Voyager has already covered. The consensus among scientists is that no such mission is realistically on the launch schedule in the near term, which means that when Voyager 1's nuclear battery finally falls below the threshold required to sustain even its last two instruments, when the plasma wave sensor goes quiet and the magnetic field detector shuts down for the last time, we will have lost our only ears in interstellar space, possibly for a generation. And the hum will keep going. Whatever is producing it will not pause for our power budget constraints. It will not wait while we negotiate funding for a successor mission. It will not slow down for the politics of space agency budgets, or the attention spans of news cycles, or the difficulty of explaining to non-scientists why it matters whether a 49-year-old probe keeps functioning for one more year. The hum was there before Voyager arrived to hear it. It will be there after Voyager goes silent. The only question that actually matters at the end of all of this, is whether the next time we manage to send something far enough to listen, we will recognize what we are hearing, or whether we will arrive at that frequency, build instruments to measure it, and find that what we assumed was natural plasma vibration has a structure too precise, too regular, too mathematically deliberate to have emerged from chaos alone. That question does not have an answer yet, and the only machine that could help us find one is running out of time, 25 billion kilometers away from the nearest person who could help it. Its signal crawling home across 23 hours of empty space, carrying data from a place that no human has ever been and may not visit again within our lifetimes. Voyager 1 is listening right now. At this exact moment, as you read this, it is out there in the dark between the stars, its plasma wave sensor pressed against the fabric of interstellar space, recording a hum that has been vibrating since long before Earth existed. And in 23 hours, whatever it heard 7 minutes ago will arrive at a dish antenna in Canberra, Australia, and the engineers at JPL will open the file and stare at the data. and the hum will be there, exactly as it has been every time before. Persistent, narrowband, structured, and not yet fully explained. The real question is not whether we are listening. We are. The real question is whether we are ready for what the listening eventually reveals. Because out there, in a silence so deep that even light takes a day to cross it, something is making a sound. And Voyager 1, this 49-year-old machine built with slide rules and ambition and the audacity of a species that refuses to accept the limits of its own reach, is the only thing we have ever made that can hear it. What happens when we finally understand what we are hearing? What happens if the structure in that signal turns out to be something more than thermal noise? What happens to every assumption, every model, every carefully maintained certainty about our place in the universe if the hum has a pattern that plasma physics alone cannot generate? Nobody's asking that question out loud. But somebody, somewhere, in a quiet office at the Jet Propulsion Laboratory or a late-night shift at Cornell University, is looking at the waveform on their screen and thinking about it. And the fact that they have not yet given us a complete answer, the fact that the papers hedge and the briefings stay carefully neutral and the official language stays precisely calibrated, that is not reassurance. That is the sound of very smart people choosing their words with extraordinary care. And that, more than any data plot or frequency chart or power management update, is the detail that should keep you awake at night.